Welcome. We are looking at variational calculus and we want to understand why variations are important when we are trying to do phase field models. So, one of the things that we did earlier was to look at the diffusion equation, and we tried to motivate the diffusion equation, and we said that spontaneous processes are processes in which the free energy is always getting minimized. So, when you have this free energy versus composition curve, when you look at its minimization, which is what should automatically lead to diffusion, we find that whenever this free energy versus composition curve has a concave region, in those regions it looks as if the diffusivity has become negative. We have found an explanation for this. We realized that the Fick's law as it is written has to be modified. We have to say that the flux is proportional to chemical potential gradients instead of saying concentration gradients. If you do that, you can explain the negative sign that the diffusivity picks. Basically, it comes from the curvature of the free energy versus composition curve. The sign of curvature actually matters. So, if it becomes negative, then it looks as if the diffusivity becomes negative. If that is all there is to it, then you can go with, so we wrote free energy, which was the classical regular solution free energy, which was something like this. So, we wrote it as x into 1 minus x with some omega parameter plus RT x ln x plus 1 minus x ln 1 minus x. So, this is basically a polynomial in x. So, the minimization meant that dou g by dou x is equal to 0, and we did all this and we found out the miscibility gap and all that. The curvature of this will have a negative sign in when omega is positive. You can find regions where that would become positive, that would become negative, and that would then lead to what is known as spinodal decomposition. We saw all that. But there is a problem, because if the diffusivity becomes negative and if you solve the classical diffusion equation, that is what you derive from the Fick's law, that is modified Fick's law even. So, you assume that flux is proportional to chemical potential gradients and use mass conservation, you end up with the same equation, dou c by dou t is some modified whatever diffusivity times del squared c by del x squared. So, in this case you find that because diffusivity is negative, any fluctuation that you put, any noise that you put is going to grow, and then the even very small noise, the noise with very small wavelength will grow. In fact, smaller the wavelength, faster would be the growth rate, and this leads to a case where you might have very small wavelengths, composition fluctuations growing. Now, the natural end of this process or conclusion that you derive from this process is that if suppose you have a system in which you have A and B atoms and they are going to phase separate, in the spinodal, then you will see that they are all A atoms on one and all B atoms on next plane, all A atoms on next plane, all B atoms on next plane, etc. So, this is like the ordered structure. So, this happens only when omega is less than 0. So, we started with a case omega is greater than 0, because that is what is related to spinodal, and we write a diffusion equation and we solve it and we end up with a solution which corresponds to this case, which is the ordering case. So, this was a problem, and this was a problem because the one of the important pieces of physics was left out, and that piece of physics is related to interfacial energy. Right? What is interfacial energy? It is the excess free energy associated with interface, and when we wrote this free energy expression, we never considered the fact that if you have a two phase system, suppose all A rich and all B rich, wherever there is an interface between the A rich and B rich region, that interface is also going to contribute to some free energy. We neglected that part here completely, and that is the reason why we ended up with this contradiction, because now this in terms of pure A, pure B, if you think of it, this is all pure A, this is all pure B. So, this is basically a AB interface, and omega was positive because the AB interface had higher energy, and that is what happens in the interfaces, and we have completely neglected that physics, and that is why we ended up with this problem. So, there was an attempt to correct this, as I have discussed earlier. So, Hillard's work on atomistic calculation showed that this interfacial energy has to be incorporated, and Kahn and Hilliard basically did that. The way they did that was to say that you have to consider your free energy as a functional, and so they wrote it in the classical functional form by saying that this free energy functional, so let me call it as some f is a function of x, y, z. Okay, previously we had one independent variable, time or x, like that, but now you have x, y, z because in 3D. So, composition is a variable, which is what we are looking at, which is the parameter, and which is what is called x here, let me call it c here, and the gradients in composition. So, composition wherever it is constant, that will be either A rich phase or B rich phase, and wherever composition has a gradient, wherever it is changing from A rich to B rich, is basically the interface between A rich phase and B rich phase. So, we can then have, so dou c by dou x, dou c by dou y, dou c by dou z. And we do not have to stop here, you can of course have higher order terms. So, you can have del squared c by del x squared, del squared c by del y squared, del squared c by del z squared, del squared c by del x del y, del squared c by del y del z, del squared c by del z del x, etc. Okay. Now, what we have is a functional, so integrated over the dx, dy, dz, right. So, that is, so this is some x point, 1 point to some x2 point. Okay. So, the integral over the entire domain, because this is a volume integral, is what is going to be the free energy. So, instead of a function, the free energy has now become a functional. It has become a functional because previously it was just a function of composition, but now it is a function of composition, its gradients, its curvature, and so on and so forth. Okay. Now, how do we deal with this quantity? For doing that, we and let me also write it in a slightly different form. So, I write this free energy functional as x, y, z, c, and del c and del squared c, etc. Now, del c is basically a vector. Why is it a vector? Because del c includes dou c by dou x, dou c by dou y, dou c by dou z, right. In other words, if I write it as dou c by dou x I, it is a quantity with one index. So, x, y, z I can write as x I, c is a scalar composition, and del c is dou c by dou x I. So, that becomes a vector. By the same token, del squared c is nothing but del squared c by del x I del x j. Because it is a quantity with two indices, it is going to be a second rank tensor. So, this is f, and we have the free energy functional, which is basically integral over the volume, and remember this is a free energy. So, which means this is a scalar quantity. Suppose if I Taylor expand this, what does the Taylor series expansion look like? So, let me take f and let us assume that it is not an explicit function of x, y, z. So, it is a function of c, del squared c, etc. So, what does this quantity look like? So, this quantity is some f of c plus dou f by dou del c into del c plus del squared f by dou del squared c del squared C plus del squared f by dou del C and del C squared plus etcetera. There are other higher order terms. Okay. So, now if you take f which is a scalar and if you differentiate it with respect to del C which is a vector, you get a vector and that vector dotted with del C is going to give me a scalar. In this case, because this is going to give me a second rank tensor, I have to do a contraction with respect to two indices to get, because this is also a second rank tensor. So, second rank tensor inner multiplied with another second rank tensor is going to become scalar, and this is another second rank tensor multiplying another second rank tensor, etcetera. Now, we are going to use all the properties that we had derived. So, what is dou f by dou del C? You can see that it is a first rank tensor. Okay. So, what is this first rank tensor? So, dou f by dou del C, which I am going to write as dou f by dou and then dou C by dou x I. So, I am going to call this quantity as some alpha I. It is a quantity with one index. So, it is a vector. Now, let me consider this quantity del squared f by dou del squared C. I am going to consider this quantity, sorry, del f by dou del squared C. So, this is del f by dou del squared C by del x I del x j. So, this is a quantity with two indices, and so this scalar when it is differentiated with respect to two indices is going to give me a second rank tensor, let me call as beta I j, and then I have another second rank tensor del squared f by dou del C dou del C. Okay. Now, I have made a mistake here in the earlier version. So, this should not be del squared, it is del f by dou del squared C. So, del f by dou del C I am going to write it as del squared f by dou C by dou x I and dou C by dou x j. So, let me call it as some gamma I j. So, it is also a second rank tensor. So, these quantities when this alpha I is dotted with dou C by dou x I, that will give me a constant, and this is dotted with del squared C by del x I del x j, that will give me a constant. So, that will give me a scalar, and similarly this dotted with this will give me a scalar, and this dotted with del squared C by del C squared, that will give me a scalar. So, now these are now properties. So, this is a free energy, the derivative with respect to the concentration gradient is first rank tensor. Suppose if I assume that I am dealing with a material which is say cubic or isotropic with inversion symmetry, then we know that all these odd rank tensors should be 0. Similarly, if I assume that I am looking at an isotropic or cubic material, then all these second rank tensors should become isotropic. So, this is the reason why we were looking at the properties of materials, tensor properties of materials and their representation in crystals. Okay. So, the underlying symmetry, okay, this quantity for example, you can already see has this intrinsic symmetry. It does not matter whether you call it Ij or Ji. That is because when you take the derivative of composition with respect to xi, xj, that is the same as del squared C by dou xj by dou xi, provided the composition field has certain continuity properties, which we will assume, because composition is a continuous field which is varying for all times for all positions, and so it is smooth enough that you can take so many of these derivatives. So, the continuity properties are there if you assume that beta ij and beta ji are basically the same, and the same is true with gamma ij also, whether it is dou by dou del c by dou xi or and dou del c by dou xj, or you call it dou c by dou xj dot dou c by dou xj, it does not matter. So, the gamma ij also has some intrinsic symmetry. So, this is intrinsic symmetry, symmetry which is already existing with respect to this property. So, these are second rank tensors, because ij is ji, these are symmetric second rank tensors, and then, so this is the intrinsic symmetry. Then by assuming something about the underlying crystal in which these are defined, we can get some more of these properties of these materials, of these material properties in these systems, which is what we will do in the next lecture. So, we will take it up from here. One can already see that in the free energy functional, the first term which gives rise to an odd rank tensor is going to be 0 if we consider systems with inversion symmetry, and if we consider cubic or isotropic systems, the second rank tensors which are also symmetric are by definition isotropic. So, there is only one constant that is associated with them. So, with this will be the starting point for our next lecture, where we will try to derive the modified diffusion equation, which is known as the phase field equation or Kohn-Hilliard equation. Thank you.